Please, Tanya.
Hello.
Thank you.
Yeah. Thank you very much for the introduction, and thanks for inviting me to this quite exciting event. It's good to see that science continues, and despite the hard conditions we see nowadays. The topics I think are very important nowadays and also become more important in the future. So I will try to share now my presentation. Let me see. Oh. Okay, can you see the presentation?
Yes,
Okay, very good. I cannot see you, so if something goes wrong, you need to, or if you have some questions, you need to raise your voice, but I guess it's okay. Okay, so welcome to my talk. My talk is about malware communication in critical infrastructures, and my research field is the detection of malware communication in the network traffic that we see in critical infrastructures. I will start with mentioning a few general challenges that we face if we want to detect such malware communication, and then we'll go in depth into particular problems we have because malware communication can hide in certain, using different hiding techniques. As you all know, we have many different critical infrastructures. That means infrastructures which are very important for the society in a sense that if they are destroyed or if they are not functioning well, that then this becomes a problem for the society. So we have critical infrastructures in the different domains like health, transport, food supply, water, media, and so on, the government, of course. And in my talk, I will especially look into the energy networks and the combination of the energy network with the communication network. Of course, the communication network is also a very important critical infrastructure, and that's also my field of research. And I see it somehow in the center of those critical infrastructures because it's important to support the other infrastructures. Especially with the energy network, with the power grid, we more and more see smart grid developments where we have sensors in the electricity grid in order to see stability issues and so on. And we have a strong relation between the energy network and the communication networks, because if we don't have power, then communication also is difficult. But also if we don't have communication, or if somebody tampers with the communication, it can harm the energy networks. Why do we need the smart grid? So why do we have communication, or why do we need communication in the smart grid? Well, first of all, for the grid operation. So we see more and more the integration of renewable energy sources, so which are often quite volatile. That means you cannot predict very well when, or can just predict to a certain extent when you have energy. And also a decentralization. That means you have a photovoltaic maybe in your home, and this gives some problems with the network. So we need to monitor the network, the grid network, the electricity network, in order to see if there are any stability issues. The second thing we want to do is demand-side management. So we want to encourage people for using the energy when it is there and when it is cheap. So we want to use flexible tariffs, or want to control home appliances based on the supply we have. One field which is coming more and more is e-mobility. That means electric cars. We see more and more electric cars. And then you can imagine that demand-side management is very important because if many people at the same time come at home and charge their electric vehicles, then this gives some peaks in the demand side. The problem that we have with if we put communication networks in place there is that, of course, we can get cyber attacks. So you can think of attackers who manipulate sensor values or modulate demand patterns in order to pretend that something is there which is not. So you can invoke wrong control decisions by the control centers, or you can even lead to instability, frequency instability, for instance, or if you compromise devices, which often attackers are targeting, then you can have blackouts. And we have seen in the past several events where this happened because of cyber attacks, that blackouts happened. So therefore, we have very high security standards if we want to kind of deploy the communication in the smart grid. We use security protocols more and more, and also classical internet protocols, IP, TCP, in those environments, and the according security protocols. And also we make use of digital signatures. This is a very good development so that we see more and more security measurements. But as we will see later in the talk, also those security measurements can be misused by attackers in order to invoke some malware communication. I give you two examples for communication in the electricity grid. Of course, you all know smart meters, which are communicating to some metadata management, but we also have more fine-grained measurements in the electricity grid, like phasor measurement units. Phasor measurement units, or so-called synchrophasor measurements, are very fine-grained measurements about the sinusoidal signals in the electricity grid. And we want to check if there's a phase shift of those signals if we measure them at different locations. And if there's some large phase shift, this can be a hint that there is something wrong in the network and that we need to do some countermeasures in order, for instance, to prevent a blackout. So those measurements are very fine-grained, a lot of measurements there, and they need to transmit it to some control center, and therefore often over a wide area network. So here you have typical structures like that you have at a substation, that you have multiple phasor measurement units, which report then to a phasor data concentrator, which concentrates the information, aggregates it, and then maybe there will be a super PDC further integrating data or aggregating data, and then it's transmitted to a wide area network. And then a control center, based on the situation that it sees from those phasor measurement, can invoke some control decisions in order maybe to prevent some blackout. You can imagine what can happen if you have here somebody is possible of tampering with the data or can kind of control one of those devices, or here on the way from the device, from the measurement to the controller can somehow tamper with the data, then we might invoke wrong control decisions. Another example is e-mobility, which we see more and more. And we have this is a picture from a project which we worked on those, on security in those architectures. And we asked the project partners to kind of sketch how the architecture looks like and what protocols are involved. And this was kind of the result that we saw. So you see here different, like the charging stations for the electric vehicles, and then they report to a charge point operator. They need to authorize themselves that they're allowed to charge, maybe with a payment card. You also could have roaming scenarios here, and you see that there are a lot of different stakeholders involved and a lot of different protocols that you have here. You can imagine that it's very hard to ensure security in such a complex environment. So if you look into the attack surface that we have, for instance, for the smart grid, and we see here like an attack tree, where we can say maybe the ultimate goal of an attacker would be to provoke a blackout. Now, if the attacker has only physical possibilities, of course, the attacker can cut transmission lines or physically manipulate some breakers and so on. For this, he needs to gain some physical access to those devices. However, if we have the smart grid connected with internet technology, we have much more possibilities to attack the electricity grid. We can kind of compromise some devices. We can use devices on the way from the measurement to the control center, or kind of changing the control commands, for instance. So here, the attack surface is much larger. So now the question is, why do we do cyber attacks, or why are cyber attacks so attractive for attackers? Of course, we see a lot of conventional attacks on critical infrastructures, of course. But if there are cyber attacks, you can do those remote. So you can attack the physical infrastructure via the cyberspace. You can control it from remote, and that means you do not need to send somebody there. This also, you have a lack of attribution. That means you can conceal who you are and what is the origin of the attack, or even pretend that you're somebody else in order to invoke some conflict, for instance. Another thing, what we see in such critical infrastructures very often is that we have a quite homogeneous infrastructure. That means you have many, many different sensors of the same type, for instance, like those phasor measurement units, smart meters, or electric charging stations, for instance. And here, if you find one vulnerability in such devices, then you can compromise many of such devices. We did some time ago some simulation of different architectures that you can use. And if you have here the devices interconnected in different networks, and you have a worm spreading there, you can see that the spreading of the worm in this simulation gets quite fast. An additional thing is that you have limited resources available. So sensors should be cheap, for instance. And then it's very hard to deploy modern cryptography in this. If you have memory and computing power, not so many resources for this, then it's hard to deploy security measures. And a third thing is that you have very old devices in the field. Usually they are targeted for like remaining 10 years in the field. And then you can imagine what happens if an attacker with a 10 years advantage can kind of do what kind of harm such an attacker can do. So cyber attacks, this is very tempting for attackers and for attackers which have a lot of resources like nation states or terrorists. Another thing which we need to keep in mind if we have cyber physical systems, that we often use state estimation, for instance, using Kalman filters and so on, for predicting what's going on in the network and if the values are kind of okay. And you can use, for instance, the residuals from the Kalman filter prediction for detecting if there's some bad data and so on. And if this is used, you can use this, of course, for detecting some anomalies, but it's also easy for an attacker kind of to trick the system. So here we try to increase the voltage values. We increase the measurement values, not the voltage itself. So we just pretended that the voltage is increasing. And if we do this slowly and with some noise over this, then we will not see this in the detection. We just see here those large outliers which were not caused by us. So the question is, like, it's attractive for attackers, and many times we see so-called advanced persistent threats where attackers remain a long time in the network in order to prepare and to do some more research on what's going on in the network in order to prepare attacks and then launch a controlled or timed attack. So the question is, maybe attackers are already in the network and spread their malware there. So we can, of course, prevent attacks, which is very important, that we have updated software, that we use security protocols and so on. But nevertheless, we always can have zero-day vulnerabilities because software can have errors, and also humans can make errors in choosing bad passwords, for instance, and so on. So if attackers are active in the network for quite some time, we can try to find out if there's some activity going on. They try, of course, to remain undetected, but malware also needs communication to spread, for instance, and therefore we have maybe a chance to detect this. And this is my main field of research, the detection of anomalies in this network traffic. So if we look into the malware lifecycle, we see that there are different phases in which malware needs to communicate. For instance, the reconnaissance, checking out for new victims in the network, infecting other machines there, spreading the malware in the network. Also data exfiltration, so exfiltrating some important information from the network, or also establishing botnets or command and control infrastructures for steering further attacks. For all this, the malware needs to communicate. So if we have the security measures, of course, I said, like, prevention is very important, secure protocols, awareness also for the humans, checking the configuration, doing firewalling and so on, and having all the software up to date. But also we need the detection part, because for the prevention, we only can prevent attacks which are known or which we can easily predict somehow. And with the detection, we also can capture novel attacks in a way that we can see if something deviates from the normal behavior in the network, and this could be then attack or attack preparation activities. Of course, if we found an attack, if an attack went on, we should do some forensics in kind of seeing what happened and then taking the attack patterns that we detected and taking them into account for the prevention then. When we look at malware communication, we see that the malware, of course, evolves. So attackers also learn a lot. And here you see part of a list that we did on different botnets that we have seen over the many years. And you can see that, like, in the past, they often used the IRC protocol, but nowadays they use very common protocols like HTTP or HTTPS, which are usually often okay for the firewall. So the firewall lets this information through. And you see also that more and more malware is using encryption, like here the transport layer, security protocol, and so on. So with this, it becomes very hard to distinguish the normal encrypted traffic, which is of course very good, especially in critical infrastructures. We use encryption and authentication more and more. However, then to distinguish if a flow is malware, if the communication is originated by malware, or if it's from a legitimate, or if it's some legitimate communication, is very difficult. So the attackers try to avoid the detection and try to look as normal as possible, like the existing communication patterns. So when we want to detect this malware communication, we face a lot of challenges here. So the normal detection part that we do, we have here the network traffic. We observe the network traffic in the network. And then we can already filter something, saying we are just interested in particular data packets there. And then can also aggregate this information into flow data. Let's say we aggregate all packets from one source to one destination because it's the most interesting for us, like for instance, from those sensors in the grid to the control center. And then comes a very important step, that is generating a feature vector. That it means, what do we give the detection algorithm as input? So here we extract information like the number of packets or packet sizes, or also well, where they are located and so on, or some statistics about those flows that we see there. And then we have the detection algorithm, which can be different kinds of detection, just looking for particular signatures, simple statistics, for instance, but also more and more machine learning is used in this domain. And then we get the decision, which is no attack or attack, but also could be a level that you say 60% attack, and then a human would need to look again into this data. We see, as I said, more and more machine learning based detection. Here, this shows a statistic about like papers that we checked in the past, which did different machine learning technologies for network traffic analysis. And you can see that many of those use very simple machine learning methods like decision trees or random forest. And this is because those techniques are more or less explainable. So you can explain the decision that the machine learning did. And therefore, first of all, you can derive some rules from this, but also you can make sure that nobody kind of tampers with the machine learning. If you have a classical machine learning like neural networks where you don't know how the decision was formed, then there might be a problem that an attacker can kind of trick the system. However, we see here that neural networks are also used more and more just because they are so successful in other domains, and therefore we use it also for the traffic analysis. One very important thing is the feature selection. So what features do you give the decision process as input? I always make the example here with the needle in the haystack, because this is often the situation that we face looking for the malware communication in all the communication in the electricity grid. And if you have here, if you visualize here the properties of the elements in the haystack, so the hay and the needle, and you choose as features the length of the element and the diameter of the element, you can see that the needle blends in very well. You cannot distinguish it very well from the other elements in the haystack. However, if you use the features more wisely, so you say here, you check the weight of the elements, and if they are magnetic, for instance, then you can see that the needle sticks out, and that is very simple. You can make a very, very simple decision algorithm, a linear classifier here, in order to distinguish those two classes, the needle and the hay. So the feature selection is an important step in this. We looked at one data set which multiple researchers in different papers investigated regarding how good those features are to detect attacks. So this is the same data set, the same 41 features which were used in all those papers. And the authors kind of said in their paper how important they think to those features are to detect attacks. And they are the same attacks, the same data set. And you can see that here the different papers heavily disagree about this. So here you have, like, for instance, in this paper, the feature 14 is considered as having a very strong contribution to the detection of the attack, whether in this paper they say it has no contribution in detecting the attack. So it's very important, like that here you do this properly, the selection of the features, in order to then later feed your detection algorithm. Another challenge that we face is we often have more and more encrypted traffic, network traffic. This is very good. So as I said, in the critical infrastructures, we need this traffic needs to be encrypted and authenticated, that we can make sure that nobody tampered with the data, or that nobody finds out about, for instance, if you have the phaser measurement units, if it's not encrypted, you might find out about like the device, where it's located and what kind of firmware it has and so on. So therefore, it's a good development that we see more and more encrypted and authenticated traffic. However, with encryption, it becomes harder to distinguish. So the malware communication from the legitimate communication, and we do not have all the features available that we have. For instance, if you want to look into the transport port, which is part of the TCP header in this IP packet, it is available if you use transport layer security encryption, but it's not available if you do IPsec encryption. So it depends on the security protocol you are using, what kind of features you have available. We looked into detection methods, just using features which are available in encrypted traffic. And here we made an approach where we use different granularities. We called it a multi-key approach, where we use different granularities of the flows. So let's say I want to check all the communication that comes from one computer, from one host, from one sensor. Or in addition, we look into the communication from this sensor to other machines and so on. And with this, we could achieve quite good results, although we only looked into features which are available even with encryption, like the packet sizes, the packet timing, and things like this. And then also what we often want to do is to have online detection. So we are dealing with streaming data. And with streaming data, situations can happen that you're online you have your detection machinery going on. And here you need a sliding window in order to see what you have seen before, and then to decide if then the data point is an anomaly or is normal. And if you have, for instance, a sliding window only quite short, and then you get a new data point, you would think that this was an anomaly because you just see this cluster here. Whereas if you would have a larger sliding window here, you would see that here is already a cluster in the same range at this data point. And then you would think this is rather an inlier, not an outlier. Yeah? So this is kind of a difficulty, because if you do the sliding window too large, then you need more memory. And some solution might be to, or is here to define such observer points in the clustering. And then with this to make a lightweight model of what's going on in the data. And with this, you can then achieve have here this detecting as an inlier, that you know, okay, this I have seen before, and increase the detection technique. So here you can see this was the SDO stream. This was one method for the outlier detection, where we actually used this model, and which performed quite good compared to other methodologies that we have. And last but not least, if we look for detection of attacks, of course, we have an adversarial environment. So we have an adversary who wants to trick our system. And if we use machine learning, for instance, then the adversary can try to kind of modify the attack in a way that it evades the detection. So here we see the detection rates if we have unmodified feature vectors, and if the attacker do some manipulation of the feature vectors, it can reduce the detection rate immense. So here you can really reduce the possibility. These are two different data sets, and here different attacks in those data sets. So you can reduce the possibility to detect the attacks by manipulating those features here. We defined some kind of an adversarial robustness score in order to kind of see how robust certain systems are regarding this manipulation. So now I want to dig into a very big challenge that we have, and this is the hiding of the communication that attackers are doing. So here we see that there's well, you all might know steganography, and that means we conceal the existence of the message. So here, for instance, you have a picture, and in this picture is hidden a different picture. You might all have seen this. You also can see this in the network. Like, for instance, we have here it's called the network steganography, and where you can say here, instead of putting the information in the packets, we put the information between the packets. So we can say here, if packets timing is long, then it means a 1, and if the timing between the packets is 0, then this means a 0. If the timing between the packets is short, this means a 0. And this is like our technologies that attackers can use in order to convey some information in this way. An example is a SolarWinds attack, which you have heard of maybe, which was an attack of a monitoring tool, and where many US government organizations and ministries have been affected, and they use the covert channel in the DNS traffic. So those channels are very hard to detect. One question to the organizers: how am I with time? So do I still have some time?
Yes, yes, we have some more time.
Some more time. Okay, just stop me if I'm over the time. Okay, okay. So those are very hard to detect. So we have different kinds of hiding information. So the one is the covert channels. That means you hide the information, for instance, in packet headers. So for instance, the IP header where you have time to live or IP identification, or in the TCP header in initial sequence numbers and so on. So you can hide their information such that only a covert receiver will kind of get this information. You can also use packet size variation, saying large packets mean this, small packets mean this, or also timing variation. And with this, you can remain undetected you can hide in the normal traffic. And of course, if you have more and more IP and TCP protocols or even in TLS or IPsec, you can find those fields. You have this in the critical infrastructures, but also with a connection to the whole internet. So this is quite a broad infrastructure that you have to communicate for your malware. An even more concerning method is subliminal channels. You all know digital signatures, and they are an important basis for many security protocols. So they help you to authenticate the data origin. So only a machine who knows a particular private key, a secret key, can make a correct digital signature. And with this, if you have a digital signature on your data, if you think like the sensor data, you give it a stamp, a digital signature, that you know this came from this particular measurement device, from this phasor measurement unit, from the e-charging station, and so on, in order to ensure that nobody is kind of tampering with the data. So they are broadly used. They are a very important element in security protocols, and it's very good that they are broadly used. However, you can also use those digital signatures in order to hide communication in the signatures. The reason why you can use it is that signatures often use random numbers or also initialization vectors or nonces and so on, where you can put then information in it in a way that anyone who is looking at the signature would not notice any difference. So, that the covert or that the subliminal receiver can extract this hidden information from the signature. There are many signatures which are affected from this, like the elliptic curve, DSA, many high-speed signatures, or also post-quantum signatures, which have this property in it. And of course, in the security protocols, IPsec, TLS, we use those signatures. So here, in this case, an attacker could misuse even our security measures that we do for using this for malware communication. I give you one simple example for how you can hide information in the signature. Here's the El-Gamal signature, which is used in the digital signature algorithm. And here you have the two communication partners, Alice and Bob. Alice wants to generate a digital signature. She selects a prime number and a prime number P, a generator G, and then generates a random number small a, which is her private key, which she should not reveal to somebody usually. Then she calculates a capital A in a way G to the power of small a modulo P. So this is a good solution here, because here it's very hard to find the small a, the private key, if you have just the capital A, because this is would be a discrete logarithm, and this is you cannot find the small a there. So therefore here Alice just sent those parameters to Bob. These are the parameters that Bob needs then in order to verify if the signature is correct. And then she generates a signature by choosing a random number, K, then computes R and S in this way, so that those R and S here then become the signature. So then she can send the message, that could be the sensor data, for instance, and put a digital signature there so that Bob knows only somebody who knows this private key can have originated this message. And then Bob can validate, verify if this signature is correct by just doing this calculation here. So now here, if you want to hide some subliminal information in the signature, you can just, instead of choosing a random K, you can put the subliminal information into this K and then do the whole procedure as usual. And then the signature will look normal to Bob here. One thing that you need to make sure in advance, you need to share your private key, what you usually should never do. But in this case, you have some collaborator, some subliminal receiver with whom you later want to use this subliminal communication. And you need to share this private key with the subliminal receiver that he can recover the message later. And then put different messages here in this K, generate a signature, then generate the next signature, and so on and so forth. And the verification, as I said, is not affected. So for Bob, it would look like a normal signature, or anybody else on the path who can verify the signature, it would look normal. But a subliminal receiver who knows the small a can be anywhere on the path of this communication, and then can recover the subliminal message with this information he has. You can use this, for instance, for the PMU measurements. So for the phasor measurements, if you would assign all the measurements here, then you can have the subliminal receiver on the path, and the receiver here, the normal receiver, would not recognize that you are exfiltrating some information from devices in the security domain. Also for the network time protocol, so time is also, clock synchronization is also important in critical infrastructures, of course. You can use this in order to exfiltrate information there. And also in the TLS handshake, for the establishment of the secure connection, you usually use signatures just for the mutual authentication. So then you would have just a possibility per handshake, per connection establishment, to put some information in there. In this project, which I mentioned on the malware communication in critical infrastructure, we also checked other methods to kind of convey some information. And there's one very often used authenticated encryption method. You might heard of the AES encryption, and there's a AES Galois counter mode authenticated encryption, so encryption with authentication, which is used quite often in critical infrastructures or also in smart metering. And in this, you here also have the possibility to hide some information in this authentication tag. So with this, you can kind of exfiltrate information from a secure environment to a less secure environment. And also, if you think like blockchains have been a big hype some time ago, where say blockchains are used for many different things. And you can also have digital signatures in the transaction blocks here, where you can then hide information here, for instance, in the elliptic curve digital signature, which is used in the Bitcoin blockchain. You can hide messages in the signatures, and this is public. So the blockchain is public for everybody. So then subliminal receivers who are maybe a botnet, for instance, you can use this in order to control a botnet when the bots then just recover this information from the signatures. For everybody else, it would look like a normal transaction. For this, we did even a proof of concept. So we injected some subliminal message in the public Bitcoin blockchain. So if you want, you can actually extract this information from the blockchain. It's still there. And we did some hiding of this message in the signatures, in the elliptic curve digital signature. And then botnets could extract this information in order to use it for steering a botnet. And you wouldn't see any unusual transaction patterns. So it's very hard to detect. Okay, with this, I come to the conclusion of my talk. We've seen like it's very important that critical infrastructures more need communication for the operation and many future demands, like, for instance, the integration of renewable energy, but this enables the possibilities for doing cyber attacks. However, also the malware, especially very sophisticated malware, needs communication in order to establish command and control structures for steering a botnet, for exfiltrating data, or for spreading in the network. And therefore, we have a chance to detect this communication and to see if an attacker is already took hold of our network or is already spreading in the network or already is getting some information from the network, which we don't want, of course. However, the malware developers use more and more sophisticated methods. So, for instance, hidden malware communication, which is very, very difficult to detect, like the covert channels, hiding information in the packet headers, or subliminal channels hiding information, for instance, in digital signatures. So with this, they would even use our security measures, like the security protocols or the signatures against us. And then here the detection is very hard. So with this, I thank you for your attention. And now I'm ready to answer some questions if we have time, I guess.
Thank you, professors. That was very nice, very interesting, your lecture about the malware communication in critical infrastructure. I think it's what we need now, today, to keep safe our infrastructures. Please, do you have any questions, please?
Can I ask?
Of course, please.
Professor Tanya, thank you very much for your interesting and very useful presentation. My question may be related to your first part of your presentation. I mean, you talked about combined attacks on physical and cyber assets. Problem is in complexity of defense from such type of combined attacks, because in this case, in point of view theory of a complex system, we need find balance between attackers and defenders. Hence, complexity of defense increases more and more. What is your opinion? How we can methodologically decide this problem?
Mm-hmm.
Because I understand that my question is very general, but I think it's a very important question.
It's a very important question. Yes, I absolutely agree. And the problem is that the systems get more complex, so that we have more and more, if you have seen like many different protocols in place, and then many different devices are interconnected. And often, well, it's good to have more simpler systems in a way that we, for instance, agree on certain protocols. So standardization is very important. And we have seen, especially in the domain of the energy networks, that when the smart grid development started, that there many different protocols were used, and also the developers of the electricity grid, they were not so skilled in the information technology. And actually, I was attending a call like 10 years ago with the IETF, this is the Standardization Organization for the Internet Technology, and with NIST, where they kind of talked about like how can we ensure more, protect more the smart grid, for instance. And it was even very hard, like the different standardization organizations, they spoke a different language, I would say. So a network for the electrical engineering part is the grid network, for the communication network people it's a communication network. But now we see a good development in a way that we use the internet protocol technology, IP, TCP, where we have a lot of knowledge what's going on, and where we have a lot of security measures which have been proven in the past. And if we kind of simplify the systems in this way, that we agree on common protocols, then this would help already with the complexity, I would say.
Thank you very much for your answer and for your presentation on more. Thank you.
Can I ask one more question?
Yes, please. Yes, please.
Thank you very much for your presentation. It's Alexander Lubimov from National Aerospace University. I'm representing both academia and and industry.
Mm-hmm.
You might heard about apparently zero-day exploits, and in my opinion, kind of filtering or filtering the traffic and trying to figure out what goes wrong is really good thing. But when I look into the fraction of root causes of systems being non-protected, I can see more and more I would say, intervention of security gap problem using open source software,
Mhm.
which everybody apparently wants to use today. So how do you see this trend, and what is your recommendation? How to attack this problem for, especially for the industrial systems?
So you mean like, should we use open source systems, for instance, where everybody knows about the software?
Well, apparently we have, because we
Mhm.
have to, because that's what industry demands. My question is, how would you recommend to, to undergo specific assessments, or, what is your take on this problem?
Yeah, well, first of all, like using open technology is the key, I would say, because you have seen like that if you use some protocols or technology which nobody is aware of, then of course you might say people don't know the specification and therefore cannot attack it so easily. But on the other hand, if you really want to attack it, then you can find 0 days, and then you can find probably more 0-day vulnerabilities than in software which is open. So definitely it's a good development that we have open software, and that we have all the standards open, and that people can have a look into this, because the more people look into this, the better. We have seen even with the open SSL bugs, like that even software which is open source, which has been around for more than 10 years, that even there you can find vulnerabilities. So this is a good trend. You have to kind of work together with different, you have to bring together different parts. The network detection is just one part which you can do, where you can say if somebody is communicating, but of course you also have on the system where you need to see what kind of log files do I have, and combine this together. So this is maybe the thing how you can tackle this. And also, the 0-day exploit, you can sell them quite expensively on the internet, and then it's also for the industry maybe important that they, there's bounty hunts where you kind of give money to people who find vulnerabilities, and this is of course difficult to pay more than the bad guys would pay. So this would be also a possibility to kind of try to tackle this problem.
Thank you very much. Well, I got another one here. What I hear from the industry quite often is that, the communication modules that industry try to use as kind of, off-the-shelf products. When you need to communicate, IoT products, Wi-Fi, Zigbee, whatever else you can use, everyone wants to have, ready-to-use solution to be able to integrate, to, decrease time to market and stuff. And quite often what I hear from my clients is that how we guarantee that all those, Chinese authentic products, that they're not sharing the data with, with unknown domains, so to say. We apparently want to communicate from point A to B, and we don't want this, parasitic traffic to be generated to somewhere we don't expect sended traffic to. How do you see this problem? Do you see the generally the problem of industry not believing those vendors from China, or how it develops?
Well, I think it's very good that vendors should not they should not believe in, like, well, you should be very careful with whom you cooperate, and well, especially like exfiltrating information that you don't want to be exfiltrated. You can of course monitor devices, but it's very important, like with whom you do your cooperation, I would say. And I think it's good that industry is aware of such things, because you never know if somebody kind of incorporated some backdoor somewhere in the software, and then can harm all your systems, or even hardware. You can have hardware Trojans in the hardware design, which is very hard to detect if you have in the hardware already some malicious part, and that can become active, and then if you think of like long or large installations like the electric charging station, or well, we have the discussion with Huawei in the 5G network. So you know that several countries kind of don't want Huawei technology in the 5G network, and maybe for a good reason. Yeah, so you never know. You need to trust your partners. And therefore, I think it's good that industry is absolutely aware of this. Of course, it might mean that the costs are higher, But if you think of the costs, if some vulnerability or some backdoor is in such of those systems, they will be much higher. So security costs something, but it's very important to invest in this, I think.
Thank you very much.
Thank you very much, Professor Sebi, for your participation, for your lecture. It's very, very important, all of these things. Thank you very much. So